All right, so in the next portion of today's lecture, we're going to talk about loss functions. So far, we have our picture of a computer program that maps our inputs to our outputs, and we've decided that our outputs should be probabilities, and we're going to use the softmax to produce those probabilities. So our function has learned parameters. If we're classifying between cats and dogs, we have a theta dog and a theta cat. But in general, we don't care so much as to what those parameters are. It's just some big parameter vector theta. So the next question we have to answer is, how do we select theta? Taking a step back a little bit, this process that we're going through is actually a very common method that we use to formulate machine learning algorithms. I can call it the machine learning method. Again, the method for solving any problem you might ever encounter in machine learning. It's a 3-step program. It's actually 4 steps, but only 3 of them require your input. The 4th one the computer does for you. So the first step is to define your model class. Essentially, how will you represent your program? And we mostly did this in the previous section. Now, there are many other model classes we might choose, many other kinds of programs. We made one particular choice, so we're kind of done with that step, but we'll talk about other choices in later lectures. By the way, when I say model class here refers to the set of possible programs that can be represented with your design and possible settings of the parameters, right? Because different parameter settings really lead to different input-output relationships and therefore different programs. So the set of all possible things you could represent is your model class. The second step is to define your loss function. The loss function measures how good a particular model from your model class is, and thereby allows you to determine if one model is better than another model. And then you could select the best model according to this loss function. So the loss function measures how good the thing actually is at solving your problem. And the third step will be to pick an optimizer, to pick an algorithm that will actually search through your model class to find the model that minimizes the loss function. And we'll talk about that towards the end of today's lecture. And then there's also a 4th step, which is like run this whole thing probably on a big GPU or something, and then you get your answer, right? So the 4th step the computer does for you, but steps 1, 2, and 3 you have to do yourself. As an aside, this way of decomposing learning problems is closely related to Marr's levels of analysis. So Marr was a very well-known neuroscientist, and he proposed a particular way to think about cognition, which of course has been very influential in neuroscience, but has been especially influential in machine learning because it also gives us a way to structure our thinking about machine learning methods. So Marr's original levels of analysis, you can think of them as kind of a pyramid, where the top of the pyramid is computational, the middle is algorithmic, and the base is implementation. The computational level of the pyramid is kind of the why question. This is the question of objectives. What is the algorithm trying to optimize? What is the algorithm trying to achieve? The algorithmic level is the what. How do we actually, what is actually the representation of the function that we're learning? What is the structure that's going to answer that why? And what Marr called implementation is kind of the how question. How is that structure actually constructed so as to optimize the desired objective? Basically, how do you choose the what to answer the why? Now, in our terminology from the previous slide, the computational level will be the loss function, the algorithmic level will be the model, and the implementation would actually be the optimization algorithm. So there's a little bit of terminology confusion because implementation here doesn't refer to like, how did you code it up? Did you code it up in Python or in Java or something? It actually refers to the algorithm. And the algorithmic level actually refers to the model. And you'll also notice that the order here is a little different than the order that I had. I actually put the model first and the loss function second. But this way of thinking about it is also very useful. The reason that we like to draw these distinctions is because when we have these different levels of analysis, it can help us compartmentalize our thinking. It can help us to build abstractions so that we can solve the problems in isolation. Essentially, if you recognize that the optimization algorithm is a separate problem from the choice of loss function, then you can design optimization algorithms that are general that can be used with any loss function. And you don't have to worry about the loss function when you're designing the optimization algorithm. And you don't have to worry about the model when you're designing the loss function. Sort of separate out these concerns and solve each of the problems individually. Now, of course, in reality, things do tend to get a little bit coupled, but keeping this kind of separation in mind can help you structure your thinking when dealing with very complex machine learning systems. Now, there are many variants on this basic idea, many different ways to separate out the levels of analysis. You could, for example, add another base level, which is like, what kind of GPU do you run it on? Very relevant to a machine learning researcher, maybe not so relevant to a neuroscientist. All right, so this is our machine learning method, and we're going to talk about how we define our loss function next. So to start thinking about defining our loss function, let's actually start with a more basic question. How is our data set generated? What is the process that gives rise to our data set? Now, if our data set consists of pictures with their corresponding labels, the actual process that gave rise to those pictures was probably pretty complex, like involves photons and people making decisions about what to photograph and all this stuff. And, obviously it's hopelessly complex when it comes to actually trying to model it. But we can come up with a very crude model of how our data set came to be. We could say that people go and create photographs of puppies in this case, and we're going to represent that we're going to think of that as just a random process. So there exists some distribution over photographs, some P of X, and humans randomly sample from P of X when they take photographs. Okay, that's not actually how people decide what to take photographs of. It's not like you take out your camera, you snap a photo, and you get like randomly either a puppy or a cat or a hippopotamus. No, that's not how the world works. But it's perhaps a useful model, a useful and very simple model to help us structure our thinking for designing a loss function. So just assume every time someone takes out a camera and snaps a photo, they get a random photo from the distribution over possible photos that might happen. And the label dog is sampled from some distribution over labels, but that distribution is not completely random. It actually depends on the photograph, right? Whether or not a photograph gets labeled as a dog or a cat depends on what the photograph is. Now, crucially here, P of y given x is not yet our model that we learn. For now, the P of y given x is the true distribution that represents the real world. You could think of it as a decision that a person makes when they label the picture. So by the chain rule of probability, we can compose these two and generate samples, x comma y, from their joint distribution, P of x comma y, which is just equal to P of x times P of y given x. So we could assume that our data set is sampled from this distribution. Our training set consists of many tuples, x and y, x1, y1, x2, y2, xn, yn, and we're going to assume that those tuples are generated according to the distribution P of x comma y. So to make this a little more formal, what is the probability of seeing a particular training set? Well, we need to make an assumption here, a very important assumption, about how different data points relate to one another. The assumption we're going to make is that our data is what is called independent and identically distributed. Okay, what does this mean? Independent means that every xy tuple is independent of every other xy tuple. Meaning that if you observed a cat for x1, that doesn't change how likely you are to see a cat or a dog for x2. Now, is the independence assumption reasonable? Sometimes not. I mean, it's probably not reasonable if you consider one person walking around with a camera. Like, if I go to like a cat convention or something, and I take a photo of a cat, like my second photo is more likely to be a cat, right? Because I'm at a cat convention. If I were to actually sample random photographs from like Flickr or something, maybe they would be close to independent because I'm not constrained by the boundaries of physical space. In the real world, if you can consider somebody walking around and actually snapping photos, the photo they took now probably is very correlated with the photo they'll take next because they're in the same physical location. But we'll assume that's not the case. We'll assume that they're all independent. So that's what independent means. It just means that xi, yi is completely independent of xj, yj. Meaning that if you saw xi, that wouldn't have to guess what xj is, and vice versa. Identically distributed means that every xi, yi comes from the same distribution. So identically distributed means that for every I, xi, yi comes from the same p of x comma y. So it's not like you have one distribution for x1 and a different distribution for x2. It's the same distribution for each of them, and they're all independent. Okay, so if you have this assumption, then you know that you can write p of d as a product over all I of p of xi comma y. Why? Well, because that's essentially the definition of independence. Independent means that the joint p of d is formed as a product of the marginals p of xi and yi. That is basically the definition of independence. It's just like if you flip a coin twice, the probability of seeing heads on the second flip doesn't depend on the probability of seeing heads on the first flip. So if you want to know the probability of getting heads twice in a row, you just multiply the probability of heads on the first attempt by the probability of heads on the second attempt. And because it's identically distributed, that's the same as just taking the probability of heads and squaring it. Okay, so we have a probability associated with our data set. Now, we're not learning p of x comma y, we're learning p of y given x. So we can decompose this using the chain rule. And now we have a probability associated with our data set expressed as a product over all of our data points of p of xi times p of yi given xi. And what we're learning is y given x. And I'm going to call it p theta here just to emphasize that now it's the learned function that depends on our parameters. So the thing that we're learning, p theta of y given x, is a model of the true p of y given x. So it's of course not the real process by which labels get associated with images. It's a model of that process, and we're going to try to get that model to be as accurate as possible. So a good model should make the data look probable. That's the basic principle we're going to be working with. So what makes one theta better than another theta? Theta is better if the corresponding p theta of y given x makes the entire data set look more probable, if it increases p of d. So we're going to choose theta such that p of d, which is equal to the product over all I of p of xi times p theta yi given xi, is maximized. Choose the model that makes the data set look the most probable. Okay, what's the problem with this? If we actually try to use this probability as written on the slide, we're going to get into a bit of trouble. Think about what the problem here might be. If you're watching this in class, you could also type it into the chat. If you're watching this online, you could also type a comment about what's the problem, what might the problem be. So the issue here is that we express this probability p of d as a product of a bunch of other probabilities that just comes from independence. The problem is that just at a very basic arithmetic level, we're multiplying together a bunch of numbers that are less than or equal to 1. Right? Probabilities are less than or equal to 1, they're between 0 and 1. So if you take a bunch of numbers that are less than or equal to 1, let's say that your data set has 1,000,000 images. You multiply them all together, you're going to get something very, very close to 0. Essentially, this objective is numerically challenging. There's nothing conceptually wrong with it, there's nothing algebraically wrong, but it's numerically very difficult to work with because you're going to get 0. So what we can do instead is we can take the logarithm of p of d. When you take the logarithm of a product, you get a sum of logarithms. So the logarithm of p of d is just the sum over all of our data points of log p of xi plus log p theta of yi given xi. And now what we can see is that the first term, the p of x, doesn't actually depend on theta. So we can just treat it as a constant. As we change theta, it's not going to affect that term at all. So we can equivalently say that our objective is a sum over all of our data points of log p theta yi given xi plus some other stuff that does not depend on theta. So that other stuff can just be ignored. So then we can formulate the problem of learning theta as just choosing theta to be the argmax of log p of d, which is the argmax of the sum of all of our data points of log p theta yi given xi. This is called maximum likelihood estimation. Why is it maximum likelihood estimation? Well, because this log probability is the likelihood, and we are choosing theta to maximize the likelihood, to be the value of theta that leads to the maximum likelihood. Oftentimes, we will actually see this written as a minimization. This might at first seem a little silly because you just put a negative sign and then change the max to a min. It's exactly the same. But the reason that we often talk about minimizing something is because in the optimization literature, canonically optimization problems are formulated as minimization problems. It's just a convention. So because of that convention, we have this slightly weird notion of the negative log likelihood, or NLL. So if someone says, I'm optimizing the negative log likelihood, they're not trying to put a double negative in there, they're just using the convention that optimization algorithms tend to minimize the objective. So the objective is something that we minimize, and if you want to maximize the log probability, that means you want to minimize the negative log probability. So this is our loss function. Our loss function is going to be negative log likelihood. All right, so loss functions. In general, the loss function quantifies how bad theta is. And we want the least bad theta. The least bad thing is also the best thing. So, for example, we could have the negative log likelihood from before. What are some other examples of loss functions that you could think of? What are some ways that you could quantify how bad theta is? Think about that for a second. Consider writing it down or putting it in the chat. What is a potential way to quantify how bad theta is besides negative log likelihood? All right, let me give you a few examples. So first, the negative log likelihood. The negative log likelihood has also been called the cross entropy. Why is it called a cross entropy? Well, as an aside, the cross entropy is a measurement of how similar two distributions are. And the cross entropy is defined like this. You take all the possible values that the random variable, in this case y, could take on, and you sum over all those random variables, and you multiply the probability of that random variable y under the first distribution times the log probability under the second. It's kind of a funny formula, but that's called the cross entropy formula. It's closely related to things like KL divergence, and it's widely studied as a way to quantify how similar two distributions are. And now if you assume that the y's in your training data were sampled from p of y given x, that's the true distribution, then the cross entropy is approximately equal to the negative log probability of that label. Because the original cross entropy is an expected value under p of y given x, and you can approximate an expected value with a sample, and that yields the negative log likelihood. Okay, if you're a little lost on this, don't worry about it. It's just a name. So the negative log likelihood is sometimes called a cross entropy. Okay, another loss function you could have. You could have a 0, 1 loss. It's a very obvious loss function. It just says you get a loss of 1 if you got the wrong answer, and you got a loss of 0 if you got a right answer. What I have written on this slide is actually a little different. It's actually a negative 1, 0 loss. So it's a loss of negative 1 if you got the right answer and 0 otherwise. That's fine too. So I apologize, there's a little typo on the slide. So if it was 0, 1 loss, it would actually not have the negative sign and would have a delta f of x is not equal to 1. It might seem like kind of a silly loss function, just saying like 1 if wrong, 0 if right, or negative 1 if right, 0 if wrong. But it is a very sensible choice, and in some ways reflects what we actually want. If you're doing a continuous regression problem, you might have a mean squared error loss. So if you're not predicting a label, you're actually predicting a continuous valued number, you might want to be as close to that number as possible. For example, you might want to minimize the square difference between your prediction and that number. And that's called mean squared error. So very popular for regression. It turns out that mean squared error is actually just another instance of negative log likelihood, because it's equal up to a constant to the negative log likelihood of the multivariate normal distribution. If you want to check this, you could work this out as an exercise at home.